Okay, let's get started. Last time we talked about what? GPIO, right? General purpose input and output. That is the most simple really, most simple IO device. So if you use Verilog HDL, if you use this language, Verilog HDL, probably you can design that, that GPIO in 1 minute, really. GPIO, you have CPU, right? And you integrate that, together. That can be designed in 1 minute, really. Very simple device. Okay, so let's back up a little bit and let me explain a little bit detail of GPIO. Okay, so that is the environment. And let me open hardware system block diagram. Where is hardware system? Open Vivado. Yes, GPIO is, super simple IO device. So that is the hardware system we are using, right? So click on open, okay, block design. Question about lecture 해청, does memory randomization? No, memory randomization, right? Memory randomization. What do you mean by memory randomization? ASLR? Are you talking about address space layout randomization? This one, 해청? Virtual memory. So address space layout randomization. So no, it has nothing to do with IO space, IO mapped memory, right? Only just memory, right? So for code and data. Okay, so IO, device has a fixed range of memory space. That is fixed. Right? You cannot change it, right? So you cannot randomize that, mapping. Okay, thanks. Very good question. I think Hae-Chang knows a lot about operating system. Also very interested in security, I think. Okay, thanks. Okay, so that is, so, what is this? Address space, because Hae-Chang, brought up this issue. You write hello world program, right? Hello world in C program, then run that hello world on Linux. Then the mapping of the data stack gets changed every time you execute hello world program again and again. I can show you, but that is not the scope of this class. So that is one. Try to run your hello world program. Hello.c. Okay. Then inside this hello world, try to print some location of some. Try to print out some location of local variable %p. Then you can check the location of local variable inside here. Like let's say int a, right? So local this a. So a, is it correct sentence? Right. So try to check out the location of local variable. Every time you execute this hello world, location gets changed because of this randomization for security reason. hacker maybe, right? Some bad guy try to sneak into your computer and hack, this executable. So to prevent that from happening, OS is providing address space layout randomization, randomize memory, stack area, for example. Try to run the program and check out this location. Okay, so that is the LED, GPIO, right? GPIO and the switch, GPIO, and so expand this probably. We have connection. We have connection from CPU to IO device, right? Through that connection, slave XE, slave XE protocol. So CPU is providing master XE protocol, master slave. So master is generating transaction. CPU, right? CPU is generating transaction. If you execute LDR or STR, right? Memory access, then generate transaction. That guy is responding. Okay, responding to that transaction. So XE is ARMS, proprietary ARMS protocol, ARMS bus protocol, okay, protocol for communication between these two devices, right? What do you mean by communication? Read or write, right? You want to read from IO device, and sometimes you want to write, right? Read and write. So how do you read and write? So that protocol is defining detailed mechanism, right? How to read, how to write. One second. So if you expand this connection, look at this. Very detailed, right? Very detailed, but very detailed, signal, address, and data. Read data, right? Data. This guy is providing data. If you execute LDR instruction, targeting that guy, right? So very detailed signal, right? Connection between CPU and GPIO, right? So this one, read address, which location you want to access data from, right? In GPIO, you have, in our GPIO, our simple GPIO, we have only one register, or few, not one, but few, okay? The first one is data register. Second is direction register. Some interrupt related register, interrupt. So we will talk about that later on, interrupt related. So which one do you want to access, right? In the last example, we accessed that register, data register. Okay. So address, right? Address contains that information. When it comes to write operation, if you execute STR instruction, store instruction, right? You are writing something, right? Writing something to which location, right? So that address, write address contains that information. And data, read data. When it comes to LDR, right? GPIO is responding, right? Responding with the data, right? This data, okay? And then write data, right? Write data means if you execute STR instruction, then CPU should provide two things, right? Address and data, right? You are writing this data to that location, right? Write and data, address and data, right? Address and data, right? And other things are control signal. So you are doing read operation, write operation, some detailed control signal. So that is not, but this is not the, the focus our class. But I want to show you how CPU and this IO device is interacting in detail. So there should be some connection. Right? And here, so how did you how did you turn on LED? We have data register. Okay, so this one is Zinc device, right? Zinc 7000, and we have Z board. This one, Z board. On Z board, you have what? You have LED, right? You have 8 LEDs. Let me draw just one. You have LED, and that is connected through this register. And then this one. So we have 8-bit. In our case, we have 8-bit. 8-bit, right? 8-bit register. And each bit is controlling one LED like this. And you have this one. This one is controlling the other LED like this. So if you write one to that bit, okay, then you are turning on that LED. Okay, and 0, then you are turning off that LED. Okay, so this one is called the register. Register, right? Not this register, right? Okay, register, right? And how do you cook up this register in hardware? Simple, flip-flop, right? So each bit, each one is flip-flop, right? You have a D and Q and clock. And this bit, that is connected. So I'm trying to explain this one. That is connected to this node. Actually, this one. So if you write 1, okay, if you store 1 to this flip-flop, then you are turning on that LED. Okay. So try to explain a little bit detail. Handling IO device means handling IO device in software means you are touching, you are accessing those registers. So from software point of view, what you have to know is what kind of registers this IO device, what kind of registers this IO device is providing. And what is the role of each register? You have to figure that out by reading a technical reference manual. Like, click on this, then it is providing documentation, product guide. Okay, some problem. Okay, let me do it again. Okay, so that is data sheet explaining that GPIO device, right? So 34 pages. So what you have to understand, what you have to know is what kind of registers. Look at this. What kind of registers? What kind of registers it is providing? It is providing two GPIOs. So you can ignore these two probably. If you use one GPIO, okay, so look at this one here. GPIO and GPIO2. We are using only this, one GPIO. So in this class. So, okay, screen. So here, this register, offset 4, and data register. Okay. The last time I touch it, that data register, right? This data register to turn on that LED, right? And we set the direction. What do you mean by direction? General purpose, input and output. So you have to set direction. You want to use this one as an input device or output device. You have to set direction, right? Input means like this. You want to take input from the switch. So click on this. Switch, then configuration. Board configuration switch. So, in this case, you have to set direction as input, and this one, you have to set direction to output. I think here, checked, right? Or output. Okay. So you cannot change it because it is, fixed because you connected this LED, meaning that GPIO device will be used as an output device. Okay, output. You cannot change it. Right? So let me click on this switch. So all input is great, right? So you cannot change it. It is being used as input device. So direction is already set by that hardware. So that means you don't have to touch. You don't have to touch this tri-state register. If you scroll it down, okay, this one, GPIO try, some detailed information here. So depending on bit setting, that pin will be used as an output 0. If you set that bit to 1, then that output pin be used as an input. So you are setting direction, right? Direction 0 output, 1 input. But again, in this hardware system, you don't have to touch because that is fixed, right? So what you have to access is only data register. It is this simple, data register. Okay. And interrupt that will be discussed after probably midterm exam. After midterm exam. Okay. Some event happens. IO device want to let CPU know. Okay, some event happened. Okay, then okay, you need to do something. It is asking GPIO, IO device is asking CPU to do something through this special connection called interrupt. We will talk about that later on. Okay, interrupt. Very important mechanism. Okay. So think about your network interface card. So think of it as a network interface card, and NIC, network interface card. You want to send some request to CNN.com, to see the front page. Then you are storing some packet, right? CNN.com request packet. Then that is going through that Ethernet connection to the server or CNN server. Then return packet comes in. Okay, return packet, response packet. Then packet will be stored in internal memory, internal buffer of this device. Okay, then that is an event. Okay, response packet arrived. CPU, you have to do something. Okay, I have a response packet. Okay, so interrupt, something like that. Right? Okay, so that is GPIO. Any question about GPIO? Okay, now let's move on to second IO device called UART. Okay, this one is interesting. This one. Okay, Hojun, can you please?
Handling I/O devices in software. I/O devices typically provide three kinds of registers: configuration registers, data registers, status registers. Software sets up I/O devices with configuration registers before normal operation. Status registers indicate status of I/O devices.
Okay, thanks. You know, there are many different I/O devices in computer. So to run each I/O device, you have to read technical reference manual, GPIO datasheet, UART datasheet, USB datasheet, PCI Express datasheet, so many I/O devices. So sometimes it's very confused. You get lost, right? But you have to, from software point of view, what you have to know is each I/O device, every I/O device is providing these three kinds of registers. And it is so obvious. Look at this. So before, right? Think about GPIO, right? Before you use GPIO, you have to set configuration. Before normal operation, you want to use this GPIO as an input device, input or output device. Okay, you have CPU right here, CPU connected, right? Then you have to set direction, right? That is configuration, right? And serial communication. We are talking about UART here. UART, that is used to communication between your Zinc, that is Zinc, and for example, your PC, notebook computer, or notebook. So you make that connection, okay? So CPU want to send, okay, hello world message, hello world message to your notebook computer through that guy, UART, okay? So then you have to think, okay, so these two guys are trying to communicate each other, right? UART and your notebook computer trying to communicate. Then you have to set, at least two things, okay? So what would be the speed? How fast that communication will occur, right? Is it like 9600 bit per second or 11? That is typical number. That is why I'm writing this number. Second, you are transferring, you are sending this many bit every second per second, or that bit per second. So you have to set the speed, okay? That that how fast the data will be transferred. There should be agreement between these two guys, okay? So that is one configuration. Second, packet format, okay? So what packet format do you want to transfer? What packet format do you want to use? Okay. Okay, hold on. Okay, second is what packet format do you want to use? That is a speed, right? Speed, and second is a format, right? Format. So each format, right? Each packet contain each format, how many data? How many bits? 8-bit data, okay, in one packet. So next packet, next 8-bit data, and so on. So before the thing is before a data communication, you have to set configuration, operating condition. In other words, that is too obvious, right? There should be agreement between two guys. Okay, first speed, okay, and format, packet data format. Okay, so the same thing goes to here. You have to set the speed, same speed, okay, and format. Okay, so that is called configuration, operating condition. Before normal operation, you have to set these, these operating condition. That is done. That is done with configuration registers. Okay, so every I/O device names are different, but the purpose of configuration register or control register or mode register, whatever the name is, the goal is to set operating condition, right? Then then after that normal operation, using data register, you are sending, data back and forth. Okay, so you can send the data and you can receive data also. Okay, so using through that data register and status register. During normal operation, some event happens, normal event or some, abnormal event, both, right? Some event, right? So, network interface called, right? CNN.com network interface called, response packet comes in, then some status register, status bit is set. Then probably then you can send the interrupt to CPU, right? So that is normal event and some exceptional event. During this data transfer, some error happened, some checksum error happened, so that exceptional event happens. So that is indicated with status register. This hardware is checking the correctness of data through some bit, checksum bit or something, right? So again, every IO device, right, is providing these three kinds of registers. So when you read specification, IO device specification, you need to check which one is configuration register, which one is data, which one is status. That is probably big picture. Okay. The confusing thing is, IO device, each IO device is providing many different IO registers. That is confusing thing, right? Okay, so software set up IO device with configuration register before normal operation. Two obvious, right? Configuration, speed, and format before normal operation. Then during normal operation, status registers indicate the status, right? Status. It is running okay, or some abnormal exception, some abnormal event happened, right? So hardware is checking that event, and that is recorded. That is recorded in status register. So software can read this status register, then figure out, okay, some abnormal event happened. I know, okay, then I need to do something. So you read the status register and check out if that IO is working okay, or some problem happened. Okay, that is big picture. Okay, let's talk about UART. This one, Hae-chang, can you please? Okay, Songmuk, can you please?
Universal asynchronous receiver and transmitter used for serial communication, simple called serial port or RS-232, has a long history, still widely used in embedded systems designed for debugging purpose, detected as a COM port in Windows. Its original shade port has almost been disappeared in computer. Instead, the serial to USB is used whenever necessary.
Okay, thanks. UART stands for Universal Asynchronous Receiver and Transmitter. So if you look at this terminology, asynchronous, things get, you are confused, right? What do you mean by asynchronous? That means there is no clock signal, okay? For no clock is involved in, communication. So in this case, UART case, you have only two wire, okay, TX, transmission, one connection, one line connection, and RX. No clock is running between these two. No clock is not involved, then that is running in asynchronous, right? Asynchronously. Okay, if you have a synchronous terminology called synchronous, synchronous, then there is a clock signal. For example, DDR, right? Your main memory. What does it stand for? Something is hidden. DDR SDRAM. S stands for synchronous. Synchronous DRAM. Okay. So there is a clock signal. Okay. When you access this DRAM. So there is a normal DRAM, just a DRAM. In DRAM, there is no clock signal, no clock. So it is running asynchronously operating. Okay. And UART, it has a very super long history, right? More than 50 years old history, very long history, right? So I'm not sure if you have seen this. Have you seen this one before? This one? Have you seen this one? So this one is more than 20 years old computer. Okay, more than 20 years old. So this one is called number 2, right? This one is called parallel port. This one. Okay, and that is used to connect printer 20 years ago, right? So printer now that got replaced by what? How do you connect your printer to your computer? USB, right? So that got replaced by USB. Okay, and this one is called VGA. Nowadays we are using HDMI, right? Or 4K connector, right? To connect your monitor, right? 20 years old, we use VGA, this connector. And this 4 and 5, that is used to connect keyboard and mouse, okay? Now that got replaced. Keyboard and mouse connector got replaced with also USB. You have USB, right? Keyboard and mouse USB. And this one is called serial connector, 9-pin serial connector. That is used for serial communication between computers. Serial communication, and also that got removed. That shape got removed and replaced by USB. We are using USB. Right? It is very old history, but it is still very widely used. If you look at the embedded system, okay, probably you haven't had a chance to look at embedded systems, but almost every embedded system has 3 I/O devices in common. GPIO, okay, the one we discussed, and UART, this one, and timer. Every computer, every every embedded system has at least these 3 I/O devices. So that is why it's still popular. Okay. Then even though that got replaced by USB, Windows, if you open device manager, the function is still there, right? That got replaced by USB. Then if you plug serial to USB, this one. This one is serial to. Okay. Okay, this one is serial to USB connector. Okay, so let me turn on. Okay, let me show you. So you have this connection. So open. So connect that to your computer and open device manager. Okay, and then expand this. Come. Okay, so for now you have only one. Okay, you have only one COM1 port. Okay, but if I turn on this one, turn on the board, then one more, right? One more COM port. The computer recognizes the new connection I just turn on, right? And this one is connected. This board is connected to that computer. So computer recognizes that device, this IO device. Okay, serial. Okay, so we are going to use that COM4 for serial communication between JetBot and that computer. Okay, so if you turn off, then that will be disappeared. Okay, that will disappear. Okay, disappear. Okay, like this. Okay. So Windows detect serial to USB as a COM port. Okay, we are going to use that COM port for serial communication. Okay, some little detail about UART. Okay, device in Zynq device. Okay, some detail. This one, 형빈, 염형빈.
It is a full duplex synchronous receiver and transmitter. Programmable baud rate bit rate generator. 64-byte receive and transmit FIFOs. Programmable protocol, 6, 7, or 8-bit data. Stop bit optional parity set, interrupt generation.
Okay, so some terminology. Thanks. Full duplex. So what does that mean? Full duplex means it has two separate connections. The first one is TX and the other is RX. So you can send the data, hello world message, for example, hello world message. And at the same time, you can receive something from your computer. Full duplex. Okay. So it happens. TX, RX can happen at the same time, right? Because separate connection. Okay. Full duplex. Asynchronous means that there is no clock signal, right? Receiver and transmitter, receiver and transmitter. Okay. And programmable baud rate generator. You can change the speed. Okay. So I told you have to set configuration before normal operation speed. So I want to set the transmission speed to 9600 bits per second. Okay, I don't think it is too slow. So I want to set into 1150-200 bits per second. It is programmable. You can change that speed. Okay, that is called bit baud rate or bit rate. Okay, and inside this UART, you have 64 byte. So you have a 64 byte buffer. UART. 64 byte buffer. So you can store 64 characters up to, right? 64 characters, like, so one byte, right? So H, E, L, O something. So up to 64, bytes, right? Then UART will take out each byte and send bit by bit, okay? Bit by bit through that connection, this hardware, right? Then programmable packet format, right? Packet format, right? The first one is speed, the second is packet format, right? Which format do you want to use? Packet format. You can use 6-bit, 7-bit, 8-bit data format, but here we are going to use this 8-bit format. That is most popular. People use that usually, typically, right? And interrupt generation, right? Some event happens, this guy has a capability to generate interrupt to CPU, some normal event or abnormal event. Okay. So take a look at now. Let's talk about this speed and packet format, right? Packet format first. So that is if you connect JetBot to your computer through USB cable, full duplex, meaning you can transfer data and also receive data. One example, packet format, right? So time, right? Time, x-axis. And first one is the line, this transmission line, TX, at the beginning, that is high, right? Like this. If the line is high, logic level 1, then nothing happens. Then if you want to transfer data, you have to put it low, put it low, right? Okay, that is indicating start bit. Okay, then 8-bit data, D02, D7. In case of 8-bit data format, 8-bit data will be transferred. Okay, bit by bit transfer, right? First bit, second bit, this 8-bit. The first one, okay, 8-bit. Then optionally, you can add parity, okay, parity, even parity or odd parity, so that the receiver can check the correctness of the data. The data is received. So you are sending data from JBoard to your notebook computer. And this desktop computer can check if the data received, right? This data received is correct or not by checking this parity. Okay? And the last one is stop it. So that is one example packet format. Okay? And then this one is how this guy is detecting each bit, D0, D1, D2, and so each bit. Okay, so internally, in notebook computer, or it has transmitter and receiver. When notebook computer transfer data, then this guy supposed to receive the data, right? Your notebook is sending hello world, for example, hello. Then that guy is receiving data, first one. Then how do you check this, this data? How do you check each bit in data? So internally, it has a clock. It has internally, not externally. Right? Internally, it has clock, which is running 16 times faster, typically. 16 times faster. All this one, running very fast, right? So it is taking sample. So it is taking sample 16 times. Right? I think I have better picture. So look at this one. D0, D1, D2, D3, and so on, right? Start bit. So zoomed in picture, this one. Okay, start bit. Okay, zoomed in. I zoomed in here. And internally you have 16 times of super fast running, clock like this for sample, this one. So that guy is taking sample at the rising edge of the clock. I'm trying to explain, little bit internal mechanism of UART. Start bit and D0 start. Okay, then clock, internally you have clock, which is running 16 times faster than this speed, data transfer speed, this speed. Okay, so every rising edge of the clock, UART is checking this bit. Okay, checking this bit. Then it is taking midpoint. So 16 samples and taking midpoint to figure out, okay, so data. So I know, this is a start bit. So I'm trying to explain a little bit detail, but you don't have to worry too much about that probably. So internal hardware mechanism. So what it means is it is taking sample, okay, sample to figure out, okay, is it start bit? Okay, what is the first data? Is it 1 or 0? Second bit, 1 or 0? Okay, 1 or 0, and so on. Okay. Okay, this one. So internal block diagram, I ask you to read this one, specification, this one. Click on this, chapter 19. Chapter, where's your UART, this one. Okay, so that is the detailed explanation of that hardware component, UART hardware component. So try read this, right? PowerPoint. I cooked up the PowerPoint based on that, based on this. So that is the one, right? Okay, the figure and so on. Okay, so try to read that TRM, Technical Reference Manual. So internal block diagram. So there is a Zinc 7000 device, is orange. Okay, orange, and you have a CPU. Then UART, there is UART. Okay, then connection is made through this pin connection between this device and desktop computer, TX and RX, TX and RX. So you need to figure out, this one. And CPU want to talk to, CPU want to access, registers, and that is done through, this connection. You are sending, CPU is sending address and data, okay, and control signal to access those registers, okay, and it is receiving clock. Every I/O device, right? Not only CPU, digital device should have clock, even though connection itself, right? Notebook computer, UART, there is no clock involved, right? There is no clock signal between these two, but internally, right? Internally, you should have clock, right? CPU is taking clock, UART should use clock, reset, those two, clock reset. Those two are default input signals, right? You should have clock and reset, right? Every I/O device, right? So clock and reset. Okay. Then let's talk about. Okay, let's talk about some more block diagram. Okay, this one. So nothing to read. Nothing to read, meaning I don't no time for a break for me. Okay. Okay, take a look at this block diagram with connection between these two, and TX54. Okay, TX54, first input, first output, right? 54, and RX54. You have 64 byte. Okay, 64 byte TX54 and RX54, 64 byte. Okay, here 64 byte each. So you can transfer. You can store, 64 byte. Okay, 64 characters, for example. Okay, then control register, configuration register before normal operation, and status register. So you can think of it as a data register. TX54, RX54. Remember, 3 kinds of registers in I/O devices. Okay, in I/O device. So control register is what? That is part of configuration register. Before normal operation, you have to set configuration. Then normal operation, TX54, RX54, that is data register. You want to send hello world message. Okay? And the last one, status register. Okay? Configuration, data register, and status register. Okay? And interrupt generation, right? Depending on the event. Okay? And this slide is talking about setting up configuration. So before normal operation, you have to set configuration, right? So this box. Okay, this one is what? This one is how fast do you want to transfer data? This transfer speed. Okay, speed. That is determined based on what? Based on clock input. So for example, how fast do you want to transfer data? Okay, so 1152 bits per second. That means from this input, you have a clock input, right? Clock, which is running at, in our case, the clock is running at 50 megahertz. Okay, so this from 50 megahertz, what you have to do is, I want to generate 115200 hertz clock. That is the one we want to achieve, right? From this clock, we want to generate that clock. That is the one. From this one to that one, input and output. Okay, so clock is running at that speed, 115200 hertz. Then every second, right? Every second. Okay, this clock. Every second you have 100 pulses. One pulse, second, two pulse, three pulse, right? And so on, right? So every clock cycle, you are sending 1 bit. Okay, so I'm trying to explain, right? So what does that mean? What does that mean by this speed? Speed is, speed is equal to that clock frequency. You need to generate internally. You have to generate that clock, 115200 hertz clock. Then based on this clock, this UART is sending data bit by bit. Okay, so 1152. The first, this time it is deasserting start. Okay, start bit. Then whatever the data is, D0, D1, D2, and so on. So every clock cycle, you are sending 1 bit of data. Okay, so the goal is from this input, you want to generate this output clock based on something, something, right? So there is a formula we are going to use. Look at this. From this input, green, light green. From this input, we want to generate this yellow. Okay, from this input, we want to generate this yellow. This input, yellow. Okay, so then the hardware is prepared for you, right? Here you have some register, baud rate generation register. By writing some value, look at this formula, right? So that is the one. That is the one. Clock. Still clock is UART reference. Okay, still clock, selection clock. Okay, so this, what is this? This component, multiplexer, right? Multiplexer. What is multiplexer? Okay, multiplexer is selecting either first one or second one to the output. So in our class, we are going to select, this one, 50 megahertz clock. So UART reference clock is equal to still clock, selected clock. Okay, we are going to select this one. So still clock, numerator, okay, numerator and denominator, you have CD. What is CD? Clock divider, CD. Okay, so where is that located? That is in baud rate generation register. So if you scroll down, So it is talking about registers. UART is providing, right? These are registers. UART is providing. Okay. Here, baud rate generation register. Okay. So you need to program this baud rate generation register. Scroll down. Backup slide. Here, baud rate generation register detail. Here you have a CD field. Default value is this number, but you can change this one, read and write up. Okay, you can set CD with the software. You can change this value. Okay, to cook up the one. Okay. So it is all about checking out this technical data sheet. Then okay, where is it? Which register I have to touch for this one? Which register I have to touch to touch this bdiv? Okay, so according to this formula hardware mechanism, denominator is CD multiplied by this one, B division. Baud rate divider register, two different register, generation register and divider register. You play with these two registers to cook up this value. Okay, it's very simple, right? You need to cook up this output and play with the CD and div, right? So there is one. Okay, same one, same thing. Trying to explain how data when it comes to receiving data, how UART is taking out each bit from the incoming data, how to take out each bit. Trying to explain that here. So that is the one. You have a 50 megahertz input. Okay, 50 megahertz input, and the goal is we want to achieve anything is okay, but that is typically used 1152 or 9600. That is typically used baud rate. So here let's talk about this. The question is let me write down. So we have cell clock, right? Cell clock, which is 50 megahertz. And the goal is we want to achieve that, we want to create that number. Okay, by playing with CD and then div. What is it? bdiv. Div plus one. Hardware is providing that mechanism, right? So CD and bdiv. Then the thing is, can you cook up that number? Can you cook up the number from this equation? 50 megahertz. What is that? That is 50, right? 50 and 6 zeros. Then by selecting some number, by selecting for CD and bdiv, can you create that exact this number? No, you cannot. Right? So we are talking about integer, right? So that is integer, some integer value, not the floating point, right? So by selecting integer, can you create a number? You cannot. So here, that is the one we want to achieve. But look at this. Calculate CD to get this number. There is one example. CD should be 62.004, and bdiv should be 6, right? 6. Then you can cook up that number. But we have a problem. You cannot use that floating point real number. That's supposed to be integer. Okay. So if you use then 62, then actual baud rate port rate you get is this one, 1152, 07.6, sorry, 37 or something like this. Not that exact speed. That means there is some communication problem. There could be some communication problem because there is no clock involved. That problem happens, right? UART and your notebook computer. Notebook computer, you are setting 1152 BPS, and also you are trying to create that number, but you cannot. You cannot create. The actual number is 1152 what? 07.37 BPS. But notebook computer is expecting this. So there is some problem, right? Communication rate, data rate problem. So every once in a while you get some problem, right? So either notebook computer is not printing out the exact character you are sending every now and then, right? Every once in a while, not that often. So that is error rate, 0.0064% error rate. Okay, that is one. But in our experiment, there would be no problem. We are sending only short message, hello world message, right? Very short message. So there, it is rarely happens. Okay, that error. Okay. Okay, then now, it's okay. So here, for detailed information about the registers you have to touch, take a look at. So I don't want to explain everything. Okay, baud rate, generation and clock source selection. Again, we are using that output. So this output, IO peripheral clock, that is the one, UART reference. That is the one. This one, green is this one, IO peripheral UART reference. Okay. So from this hardware component, you are getting clock, right? That will be used as UART reference, which is 50 megahertz. You don't have to worry too much about these hardware block modules. And then detailed registers. Okay, some registers you have to play with. So look at this. So here in the UART, right? The UART, you have 3 kinds of registers again, right? Configuration register, packet format, right? So this orange is configuration register. Okay, baud rate setting. The yellow, that is also configuration registers. Okay, and data register, this green is data register. Okay, you want to send the data or receive data, and status registers. Okay, so you can categorize these registers into 3 groups. Okay, configuration registers, data registers, and status registers. Okay, so your job is you need to read. Okay, what is this register for? Control register 0. What is this mode register is for? You need to read the specification, right? So I have a backup slide here. So control register, what you can do with control register, you can enable or disable. You can enable, okay, this data communication. You can enable or disable data communication. Okay. And mode register, okay, look at this. You can set packet format, 8-bit packet or 7-bit packet. You want to add parity bit. You want to add a stop bit, packet format. Okay. Packet format, again, this one. This packet format. So you want to use 8-bit data or 7-bit data, 6-bit data, do you want to add this parity? This one is optional, right? You can add or remove depending on the register setting. So those things, right? And then what else? So baud rate generation register, okay? So CD, the CD, right? You can program CD in this register, and then divider register, right? This bdiv. Okay, this register is providing bdiv. So you need to write, some value here. TX-RX54 data register. Okay, data register. Then some status register. So meaning, look at this. TX, 64-byte 54. That is full. You are sending. You store too many characters. Hello world, message, some your name and so on, right? So you store too many messages. Then 54 would be full. Something like that. Okay, so then let me show you a demo. Okay. Okay, so full. So in the experiment, we are going to, we have two devices, right? JetBoard and notebook computer, right? On JetBoard side, we are going to, write everything. We are going to do everything by assembly or C. We are going to take care of everything. Okay, we are going to send some data through UART to notebook computer. But how about this notebook computer? What do you have to do with this notebook? Oh, okay. So what do you have to do with notebook computer? So notebook computer should have some kind of software, right, to receive data and display the received data. Okay, and so this software, through this software, you can send some information, some characters to this JetBoard. So you should have some kind of software running on your notebook computer, right? That is, I recommend you to use that. This one, Teratom. This one, Teratom. So download this, okay, and install it. Then you can see what is Teratom? This one, Teratom. So I already set up this one, but if you run it first time, then you have to set up using serial port. Okay, then look at this here, port COM1, COM4. Here, device manager. 2 devices. So between you need to select COM4. And look at this, a baud rate speed. I want to set the speed to 1152. PC side, right? PC side. Set up serial port. Then that is a speed, right? So from on PC side, you are setting speed and packet format, right? You are doing the same thing using that software, Teratom. Using this Teratom, you are doing the same thing. Before normal operation, you set the speed and packet format, right? What is the speed? 1152 bits per second. And this one is packet format. Okay, data, 8-bit data. You can select or 7-bit, but we are going to use 8-bit, no parity. Okay, stop bit, 1-bit, and so on. you have to set this configuration before normal operation, right? Too obvious, right? So then, so PC, right? PC is now ready to receive, or PC is now ready to receive data and send data. We receive data and send data, okay? So on JetBot side now, we have to prepare software on JetBot side, right? So you have to make UART ready for communication, meaning you have to set configuration, speed, same speed, right? Speed and packet format. And then you can send the data. Okay. So I'm providing example code here also. Example, this one. Download this. Okay, example code and unzip it. And here 1141. Okay. So and then create a new project. I already create new project for you. Okay, we have 5 minutes left. So let me do it fast. Okay, here. Let me briefly show you, then probably next time I can explain in detail about the code. So here I created this one. Another application project. I did new application project. Okay. So in the first lab, you created CSD lab application project. So probably you want to create separate, right? This one. So I added this one. This one. Simple hello world, right? The one I downloaded, you downloaded. Okay. Then so this one init that is provided in this file init. Initialization UART init. Then basically packet format, right? Packet format and speed. I want to create that speed 1152, but I cannot create that exact number. So instead, so this number would be okay. Okay. Every once in a while, there would be some problem, but that's okay, right? So I set CD and this BDIF, CD to 27, BDIF to 15. Okay. Then that is initialization. Then you want to send hello world message, branch and link. You are calling this function called UART hello, which is located here. Okay, UART hello, UART hello, simple function. Then scroll it down. What is that? You want to string, right? String. You want to send this hello world message, okay, to your PC, okay, to your notebook computer. To send a hello world message, you need to go through this loop, TX loop. Okay. Read each byte. First, read H. Okay. Using that, which one? Using that load byte instruction. Memory read byte, right? LDRP, byte instruction. Read first character and send it. And read second byte, send it. Remember this one? What is that? Pre-indexed, post-indexed, I forgot, right? Pre-index, post-index. Read data from this location, then do incrementation by 1. Okay, to point next character. What is this? Carriage return and line feed, ASCII code, right? Carriage return or line feed. So let me quickly execute this. Okay, download it to the board. Okay, so here let me download it to the board. I don't have anything to show, but okay. Here debug. Okay, so I created this hello new project, new session. Okay, you can do the same thing like this, new session. Okay, then debug. Time. Okay. Okay, so let's just skip this initialization. Okay, and set to skip that, you can set breakpoint like this. Double click this. There is a breakpoint. This one. Double click. Okay, and here take a look at this. And then breakpoint, right? So you set breakpoint these 5 different locations. Right? So here, line 18 here. I just double click this. If you double click this, then that got disappeared. Double click. Then I set breakpoint, meaning I want to press F8, okay, to execute until this point and stop the program here. Let me press F8. Okay, program stops here. Okay, then from here I want to check out this code, right? Line by line, instruction by instruction. So press F5. Okay, so register probably. Okay, so then F5, right? 5. It is checking some status register to see if everything is okay. So for now, let me just execute it. So now it is reading R1 location. What is R1? R1 location. R1 is what? String. This location. H. So R3 register will have first character H. Okay, ASCII code. Okay. 5. 48. 48 is ASCII code for this big H. Okay. ASCII table. Okay. So big H right here. Here is the big H, right? H 48 in hex. 4H, right? In hex. Okay. So that is why you have 4H, 48, 48 here. Okay. So now you are sending, look at this. Now you are sending here, store byte. You are sending this data. Okay. 5. Check out this. Check out this terminal. Okay. PC is trying to receive, right? PC is trying to receive data. Okay. Okay. Then F5. You see, H. H appears here. You just sent one first character. Okay, so let me press F5 and check out this. Look at this here. H character by character. You are sending character by character like this. Hello world. Okay. Then the last one, and this one is line feed. I think line according to this ASCII 0D 0A. What is that? 0D. 0D is carriage return. Right? D is carriage return. Return, right? You press the return key, right? And then A means line feed. Line feed. The first, first column, carriage return, and first column, right? Then cursor, right? Cursor will go down like this, and the next line like this. Okay. So play with that code, and next time I'll explain in detail about this code. Okay, Joan, you said bore rate is 16 times faster than bore rate. Why is PD plus 1? Why PD plus 1 is only 7? That is Juan, that is not the rule. Okay, that is not the rule. 16 times, that is typically used. 16 times faster. This one. So input. Input is 50 megahertz, right? And this yellow is 1152, right? And then this Bo sample clock. Typically, people want to use 115200, 16 times faster sample clock. For what? To receive data. Okay, notebook is sending data, right? And you need to extract start bit, D0 first bit, second bit, and so on. To extract each bit, you want to sample at very fast rate, which is typically, I'm not saying it is a rule, typically 16 times faster. But you can change it, 8 times faster or something, depending on your appetite. But that is typically used number, 16 times faster sample clock. Okay. So depending on this sample clock, error rate would be different also. Error rate, I think. So that is probably too much detail, right? Error rate. Okay. Okay. Any other questions? Okay, please play with a UART code, because next assignment is about using this UART to do very interesting work. I'm going to ask you to design your own debugger. Okay, your own debugger. Okay, so meaning after executing one line of code, for example, this code, you want to, this SDK is providing this nice view, right? Nice, GUI based view, R0 register to R15, right? So instead of using this SDK, I'm going to ask you to dump, okay? After executing this, code, show me R0 to R15, all general purpose register, print out general purpose register to, your computer, your notebook computer, okay? Your own debugger. that will be next assignment, and very interesting, but takes time. You have to think a lot, because you are corrupting register state, right? That will be very interesting homework. Okay. All right. That is for today. Okay. Then I'll see you next time. Okay. Bye. Thanks.